Good afternoon, everyone. This is Dr. Carlos Morillo. I'm going to be your host this afternoon. Again, thank you and welcome to our webinar series. Today, we are going to be talking about the fundamentals of FTIR. And Dr. James Burgess is going to be our presenter. I just want to make an introduction of him. Dr. James Burgess, he obtained a Bachelor of Science in Chemistry at the University of West Georgia, performing ultra-high vacuum and environmental chemistry research. Then James earned a PhD in analytical chemistry at the University of Alabama for surface science and material research using infrared reflection absorption spectroscopy, techniques in vacuum system, Raman microscopy of ferromagnetic perovskites, and fabrication spectroscopy of carbon materials. He taught a couple of years at the Georgia Southern University while completing his dissertation and applying for a postdoctoral position for the National Research Council at the Naval Research Laboratory. His work at the NRL involved functionalizing of graphene, including the first reported fully fluorinated graphene and functionalizing micromechanical resonators. After NRL, he was project manager for two SBIR projects involving the functionalization of chemical preconcentrators for the CBRNE detection. Next was FTIR Raman application focused cells using seminar demonstration experimental design, and he has been awarded 2 patents, 5 research awards, 2 book chapters, 3 grants, and 12 manuscripts, and more than 1,500 citations and 40 and plus poster and presentations. So with you, I'm going to let the floor to Dr. James Burgess. Okay, James, I'm going to make you the presenter, so the floor is yours.
All right, thank you, Carlos. So my name is James, and I'm going to be talking about FTIR theory, instrumentation, and techniques this afternoon. So just want to talk about Jasco itself for a minute. It was founded in 1958 by Drs. Fujioka and Tominaga. And Tominaga actually won the Nobel Prize alongside Richard Feynman for QED. Staff, we have 6 PhD scientists, including 2 vibrational spectroscopists, me and Carlos. We have a wide background of for spectroscopy. We have FTIR, Raman, circular dichroism, both electronic and vibrational, IR microscopes, UV vis, and fluorimetry. And today we're going to be talking about FTIR. So a little introduction to the theory of infrared spectroscopy. So infrared spectroscopy is in the electromagnetic spectrum from 2.5 microns to 25 microns. As you go from right to left, you increase in energy and increase frequency, but decrease in wavelength. So this is less energetic than this. The process in which a molecule absorbs infrared radiation, a photon comes in, it excites it to a excited vibrational state, and then it relaxes again, releasing a photon. These photons cause a change in the dipole moment of the molecule, which causes the bonds to contract and expand or move relative to their positions. The number of molecules, atoms in a molecule is what determines how many peaks are in a spectrum, and it goes 3n minus 6. So you can imagine the more atoms you have in a molecule, the more complex the spectra will be. So example of the modes that are possible for a CH2 molecule, portion of a molecule. The first is the symmetric stretch, which has the hydrogen atoms moving towards and away from the carbon at the same time. And then there is the symmetric stretch, and the asymmetric stretch is when they move away and towards, not in unison. So one will be expanding away from the carbon, the other will be compressing towards the carbon. You can see they have two different energies that are fairly close together. Next is scissoring, in which this triangle is actually the plane of the molecule of the carbon atom. So in scissoring, they stay in the plane, but the two hydrogen atoms move away from each other and then towards each other. For rocking, they actually move at the same time in the same directions together in plane. And again, they have two different energy levels, with the scissoring be a higher energy than the rocking. Next is out of plane bending, in which the hydrogen molecules go out of the plane that the carbon's in and then back towards the observer together at the same time, and is wagging. And twisting is when they move in and out of the plane, not in sync. So why do they have different energies? Well, each one of those have a different spring constant. So that's K in this equation. So this is the energy is approximately 1 over 2 pi times the square root of K over mu. So that K is the force constant, or the amount of energy it takes to move the bond. And the M is the reduced mass of the bond. So all of those modes had the same reduced mass, but they had different Ks. So if you, an example is the carbon-carbon bonds. If you increase the K force constant from single to double to triple, you actually increase the energy pretty dramatically. For mass, you can look at the CC, CN, and CO, and as you increase the mass, you actually decrease the energy. And note that the mass has less of an effect than the spring constant itself. So this is isopropanol spectrum showing the different bends and modes that are possible in this molecule. So OH stretch occurs here at 3200, and the CH stretches occur around 3000. And there's CH bending, OH bends, stretches, and bends, more bends. So each molecule is going to have its own set of peaks based on all these possible vibrational modes. And you can actually look at a spectra and decide which modes are which by looking at a correlation table. So this has many of the different types of bonds and the range where they occur. So for example, CH bonds for an alkane is lower energy than an alkene, which is a lower energy than an alkyne. So you can use this correlation chart to help understand a spectra. So now we can talk about instrumentation. So the original spectrometers for infrared radiation were all gratings based. They were dispersive. What happens with a dispersive instrument is that you have a slit that the light passes through and is focused on a grating, which is then focused through another slit to the detector. And that, as that grating moves, you change the wavelengths. So these were done because it was a simpler operation. Once computers came around, we started doing the FTIR, because the computer can actually do the Fourier-transform, which I'll talk about in a little bit. So the heart of an FT instrument is the interferometer. So as you can see, it's this is the interferometer from a Jasco system, and we have cube-cornered mirrors so that you don't have to worry about alignment in the system. So that is the moving mirror that's represented here. So with an interferometer, the light comes from an infrared source, hits a beam splitter that splits it into two parts. One part goes to a stationary mirror and back out. The other goes to a moving mirror and back out. Then it goes through a sample to the detector. And as that mirror moves, at the 0 position, you have constructive interference. and then it goes destructive interference, and then constructive and destructive as it moves. So that moving mirror causes constructive and destructive interference, which is used to create an interferogram. So this blue is the interferogram. As you can see, so this is constructive interference at the peaks, destructive interference at the troughs as it goes through. And each data point is taken where there's a crossover for this timing laser. So the timing laser is a Heaney laser that has a really well-defined wavelength so that you know exactly where these crossovers are. And each data point is taken at a crossover of this timing laser. So it's really important to have a good laser here, because if you don't, then this can cause a shift in frequency. So once it hits the light hits the detector, it gets converted to usable electronic signals. The two most common detectors for mid-IR are DTGS, room temperature detector, and MCT, liquid nitrogen cooled detector. The room temperature detector is fairly inexpensive. It works for 90% of all samples, and it's pretty much the standard with most instruments. The MCT is a lot more sensitive, a couple orders of magnitude more sensitive than the DLTGS, and needs to be liquid nitrogen cooled because the background radiation will swamp the detector. And it's good for situations where you have just a little bit of sample, so grazing angle, some gas samples, MCT is good for. So that interferogram is in the time domain. So it comes out as this is mirror position, which if you know the speed of your mirror and where your mirror is, you can convert that to time. And then undergoes a Fourier-transform, which is a pretty complicated equation that takes about a page and a half worth of calculations for each data point by hand. So this is the reason why this technique didn't become popular until we had personal computers. So as the computers got smaller, it was easier and easier to do this technique. So it uses the Fourier transform, and it converts it to single beam spectra in the frequency domain. So some of the advantages over the grading spectrometers, there's the Felget advantage. So since this light is being hit one at a time, you have to wait for the entire rotation of this grating to get a spectra. So it takes a lot more time to collect the spectra with a gratings base than this one, where it's pretty close to instantaneous getting a spectra. The Jacquinot advantage is, since there's a slit here that blocks out light, a slit here that blocks out light, multiple optics that it's bouncing off of, and you're only sampling a portion of the light that's gone through the sample. So the intensity is a lot less for gratings base than it is in FT, because with FT, you have all the light hitting it at once. And the last is Cohn's advantage. So the timing laser gives the precise mirror position and gives the instrument its precision. So your data is only going to be as good as the laser you use. So if you use a silicon diode laser, its wavelength's not as stable as a Heaney. That's why we don't use lasers that are basically found in laser pointers, because the wavelength the frequency on the laser is not steady with compared to other lasers. So this precision allows you to be able to do things like spectral subtractions, library searches, subtraction, concentration curves, any application where you have to subtract or do an algorithm match. So what is a good FTIR spectrum? What are the criteria? First, the spectrum baseline should be relatively flat, meaning it shouldn't be curved or it shouldn't be slanted. The highest transmission point should be 95 to 100 transmittance. So this is where there's no spectra, no signal in the spectra, where it should just be a flat line. There's no peaks. That should be between 95 and 100%. There should be very little noise. Most of the time, it takes less than a minute to do 16 scans, and 16 is usually more than enough on most applications. The strongest should be greater than 50% and no lower than 3 and 10%. The reason why you have to worry about it being low is because as you get lower and lower transmittance, you start to saturate the detector, which causes peak shift changes or peak shape changes. And one of the most important aspects of collecting a useful spectra is sample prep. So, and some of these I'll talk about. It just takes a little bit of patience to get the sample where it's good. So the power that comes in, I just want to talk about the units because I do both transmittance and absorbance throughout the talk, and those are the two common units that you do. The absorbance is the light absorbed by the sample. Transmittance is the light transmitted through the sample, and they're related to each other. And in software, you can go from absorbance to transmittance. You can change it whenever, whatever your preference is. Sample concentration, you can use Beer's law, and Beer's law is A equals epsilon BC, and A is the absorbance, so that's the peak intensity. Epsilon is the absorption coefficient, which is unique from molecule to molecule. B is the path length, and C is the concentration. So most of the time you can find out, you won't be able to find out E without doing a concentration, or epsilon without doing a concentration curve. So the slope of this curve is going to be epsilon times B, and then concentration. So these two from sample to sample at different concentrations won't change, but the absorbance and concentrations will in respect to each other. So you can actually take several spectra and then look at peak height or peak area, and then do a concentration curve. So this is a concentration curve for these samples, and it's fairly linear. All right, so I've been talking about mid-IR. I want to talk a little bit about far IR and near IR as well. So near IR basic. So near IR is 4,000 to 1,500. So it's the gap between mid-IR and UV vis. And there's two different types of modes. One is a combination band, which is two vibrations occurring simultaneously. The second one is overtones, a vibrational mode at the second vibrational state. And these combination bands occur at lower energies than the overtones. And the way I describe combination bands is the simultaneous, it's almost like a piano, where you have a combination band would be a chord on the piano, and an overtone would be C and high C. So the frequency differences work out that way. The disadvantage is that the modes aren't technically quantum mechanically allowed, which I always find it funny that it happens anyway. And they tend to be quite weak. The spectra are very complex usually, and a lot of times you need chemometrics to do it. But the advantages is that you have a long path length, which means that bulk properties can be measured, and it's insensitive to water. So one of the uses one of the industries that use this are food and feed industries where they have grain. And the grain has a little bit of water in it, And you want to look at bulk samples, so you just put it all in a cup and then integrating sphere, and then you can run it. So you can do quality control. So the hardware for near IR, the source is a halogen lamp, so it goes from 2,000 to 25,000. There's several beam splitters that are possible to use. So there's quartz that goes from 4,000 to 25,000. There's silicon on calcium fluoride, which goes to 1,200 to 15,000, and a KBR broadband, which goes from 375 to 12,000. And you pick these based on what you need for your application. The two common detectors are a silicon photodiode that occurs from 10,000 to 25,000. So it goes most of the range, and InGas, which goes from 4,000 to 12,000. So this is an example. So here's ethanol, and you can see it in the brandy and in a little bit in the red wine, none in the water. So you can see these are very broad features. It's not as sharply defined as you get with IR. That's why you need a lot of samples. This is an example of a calibration curve from this data using transmission. And you can see there's a very good correlation here. So for IR, it occurs from 50 to 700 wave numbers. The modes are a multi-atom bending mode and lattice vibrations. So the bending mode would be something like carbon-carbon-carbon bending. The last small vibrations would be metal-oxygen-metal. And these modes are really dependent on crystal structure. So they can shift, or you can have two modes. And it makes it very useful in being able to distinguish polymorphs and closely related compounds, which I'll show you one in a second. Water is a strong absorber, so the system should be purged or evacuated. And I'm a big fan of the evacuation for this because the water signal will affect your measurement. So the hardware. So a high intensity source, ceramic source, goes from 20 to 7,800. Beam splitters tend to be mylar, and the thickness of the mylar determines where your wavelength range is. So you can do a 50 micron thick mylar, which is 10 to 60 wave numbers, and then the broadband, which goes from 30 to 680. The detectors, you can use a DTGS with a polyethylene window that goes from 330 to 700 wave numbers. Or if you need to get lower, you can use a bolometer, which goes from 10 to 650. Note on the bolometer, that's liquid helium cooled. So it's, if you can get away with the room temperature detector, you should. Liquid helium is fairly expensive. So this is an example of two different compounds. This is barium carbonate and calcium carbonate. As you can see in the mid-IR region, they look very similar with these peaks coming out at the same place. These are all CO3 peaks, these three. So you can't really tell. However, if you look at the far IR, there's a large difference between the two compounds, and that's because it's the carbon-BA carbon bond. Again, so that was two different compounds with different metal ions. And then two calcium carbonates are here. One's calcite and one's aragonite. And aragonite has two distinct peaks in the far IR region, and the calcite has a broad peak in the near infrared, far infrared region. So we talked about different beam splitters and different sources. So if you're going to do full ranges, if you want to do far IR and mid IR, or near IR and mid IR, you need to change the beam splitter and the windows in between different methods because each beam splitter has a different useful range. So one thing you can do is actually get an automatic beam splitter changer with automatic windows, and then there's automatic detector switching as well in the bench. So these allow you to switch wavelength ranges without having to break your vacuum or purge. All right, so let's talk about some techniques. So the first one is the simplest to think about, and it's transmission. So the light hits the sample, is attenuated by the sample, and then the light comes up. So PN is going to be greater than PO. You can do solids, liquids, and gases with transmission. So this is a pellet holder. So this is a die. This is what you use to create pellets, and that's a pellet holder. This is a liquid cell, and these are long path length gas cells. So transmission of solids. So if you want to make a KBR press or KBR pellet, you get 3% of the sample in with KBR, and then you grind it into fine powder, and then there's a high pressure clamp that will compress the sample until it's crystalline. So it takes a decent amount of effort to create these KBR pellets. Another technique you can use is a diamond anvil cell, where the sample is placed between two diamond windows. So this is a diamond anvil cell here. And then that you use these thumb screws to compress the sample until it's IR transparent. So liquids. So liquid cells are comprised of has a holder and two IR transparent windows and a spacer. So these windows that you use should be selected based on the intended samples, with KBR being the highest throughput. However, KBR fogs over time because it reacts with water. So the samples must be dry, and it must be stored in a desiccator. The zinc selenide are a good alternative material if the sample has water in it. It's got a little bit less throughput. However, it makes up for it for its robustness. To determine the path length that the light goes through the samples, there's actual spacers put in between the windows, and these can go from 15 microns to 10 millimeters. A small path length, the smallest you can do is desired, is good because it's, and you just choose the path length based on the concentration of the analyte that you're interested in. Usually you have several, and it becomes a trial and error to get which one that you need to run your samples. All right, so transmission of gases. Gas samples require a high path length. So the number of atoms in gas is a lot lower than liquids and solids. So you need, a lot of times you need a high path length. You can go down to 5 centimeters if you're working with a pure or a highly concentrated gas. Lower concentrators where you need longer path lengths, up to 30 meters is the longest I've seen. I always recommend getting a heated jacket, because gases tend to, especially if it's coming from a process, if it's coming from some outside sample that you're creating, you need a heated jacket so that the gas doesn't condense on the side of the cell, because if it's condensed on the side of the cell, you're not going to be able to see it with IR. All right, so next we'll talk about specular reflectance. So specular reflectance, you have light simply bouncing onto the sample and then back off again. And its incident angle is usually 30 to 60 degrees. This is an example of an accessory. And specular reflectance is really good for coatings on things like Coke can lining. You can do specular reflectance because it's a polymer that's on a metal. So if you have a polymer on a metal, it works really well. It will work with other samples as well. One drawback is sometimes that sometimes the light will, if the refractive index is at a certain value, it will actually cause these derivative peaks. So this is actually the real part of the spectrum and the imaginary part of the spectrum according to Snell's law. And this can actually be done through the computer, through the software, and you can correct for this and get a regular spectrum. So diffuse reflectance is you have instant light, and you have on a rough surface, you'll have the light coming at many different directions, not just the specular component. So you remove the specular component out of this by collecting it with this accessory. So if you look, each one of those is a little sample cup that you put your sample on, and the light hits it, it's focused through and goes out, and the specular reflectance goes out the top. And this is good for neat powders. Not all neat powders will work. If it's too strongly absorbing, you're not going to get any signal. If it's something that's weakly absorbing, like soil, you can get good spectra off of it. The other option, if it absorbs too much, is much like when we talked about the making KBR pellet. You make just a mixture where you put 3% in KBR and you mix it really well, and then you put it in and do the experiment. Rough surfaces, if you have a rough surface, a lot of times you can get signal off of it. And then you can also use an abrasive pad where you take the pad and you scratch it onto the surface of whatever you're wanting to look at. So that's really good for forensics, where you are situations where you can't bring the sample to the instrument. You can just sample it using that abrasive pad. And then that pad's rough enough to where you can do really good drift on it. This has a small issue where as the wavelength changes, the spectrum changes with wavelength. So relative to the transmission, it looks different. So what you do is you go through Kabelka-Monk transformation, which changes not the position, but just the intensity, the relative intensities of these. And that comes out as km units. And so grazing angle is very close to the specular reflectance, only it's got 80 degree and higher incidence angle. So it has a really shallow angle of entry. And you can imagine this will actually interrogate more because you're looking at a more shallow base. So you're looking at more of the sample on the surface. This is really good for extremely thin films. It's usually low concentrations. We're talking monolayers to multi-layers. And a lot of times you have to use MCT in conjunction with it. So finally, ATR. So with ATR, you have a crystal, and special crystals, usually diamond, zinc selenide, or germanium. And the light goes in, and it bounces. The light bounces internally through into the crystal, then out. And as it's bouncing, it actually creates a standing wave where the sample meets it. So that's why it's called attenuated total reflectance, or ATR. So the sample prep on this is very easy. Most of the time, you just put the sample on the surface, and if it's a solid, you put down a clamp. If it's a liquid, you don't have to do anything. And then you take your spectrum. So I mentioned that zinc selenide, diamond, germanium are the most common. Refractive indices are about 2.5 for zinc selenide and diamond, and 4 for germanium. The penetration depth is a lot deeper for diamond and zinc selenide than germanium, which actually is an asset in some ways, and I'll get into that. The range is 650 to 5500 for zinc selenide, all the way down to 30 for diamond to 4500, and 650 to 10,000 for germanium. So germanium can even be used in the near IR. The benefits, the zinc selenide has good throughput. It's fairly robust as far as not reacting with different compounds. The diamond is very durable, of course, it's diamond. It's usually the one most people get is going to be diamond. And then the germanium is really good for dark samples. So that small path length, is actually a benefit here because the dark samples absorb a lot of the light, and the more that you go into the sample, the more light gets absorbed. So it's good for samples such as EPR, any of the carbon samples, black samples. Diamond's great for hard powders because it's, like I said, it's robust, so you can put a lot more pressure on it. And then zinc selenide is used for just general organic substances and liquids. So the only down part of diamond is that at 2000 you get it does have some absorption, the diamond does, so you have a lower signal or noise in this region. Germanium's downside is that it's got a the small depth of penetration means that you get weak absorption. So I was talking about penetration depth. So the penetration depth, the dP, is related to the wavelength divided by a relationship of the refractive indices of the sample and the ATR. So as the wavelength changes, so as you go from left to right here, the wavelength is changing, so the penetration depth is changing. And notice that the zinc selenide is changing more rapidly than the germanium. And the depth of penetration, it can be from 0.5 to 10 microns. So you have choices on ATRs where you can go from a single bounce where the light just bounces off the crystal once to multiple bounces up to 14 bounces, and the more bounces, the greater your signal. With the caveat is that it's going to depend on the size of the crystal, how good of contact do you have with the sample in the crystal. So you want the whole crystal covered so you get the maximum out of it. So I mentioned a clamp earlier. So the clamp actually presses down onto the sample to have it on the sample at an order of 1.5 microns. So the path length, it's 1.5 microns. That means the sample has to be smooth on the surface to 1.5 microns. So liquid, you don't need a clamp at all because it's already flat against the surface. If you have soft samples, you can do low pressure. That's all you need. You can get high pressure clamps if you've got hard samples. And you do not use the clamp for background. So you do the background in open air. Remember the path length is very small, so and the gases in air are much lower concentration than what you're going to see in your sample. So you don't need a clamp. You need to put the clamp down for the background. The differences that you can see, this is a carbon black filled polymer, which, as I mentioned, germanium is going to be better for, and you can really see it here with the zinc selenide. So you get these derivative peaks because, again, you're looking at the real and imaginary part of the spectrum because your sample was, its refractive index doesn't match the one for zinc selenide. However, the germanium, it comes out fine. All right, so ATR, if we look at ATR spectrum versus the transmission sample spectrum of the same sample, you can see that the relative intensities are off. So this one is higher than this on the ATR, but they're the same height on transmission. And the reason is, as we go from left to right, the penetration depth is going to increase, which is going to cause an intensity distortion, relative intensity distortion throughout the sample. So the computer can actually go back and use that equation, the penetration depth equation. So the computer can actually use this equation to solve for what the intensity should be. And that's the ATR correction. So this is a sample. Again, see these peaks are the same height. It undergoes a correction, and this is higher than this one. To do this, you do need to know the refractive index of the sample. And I'll tell you now, most of the time, for most organic molecules, it's 1.5. All right, so in summary, infrared energy infrared energy causes vibrations in molecules, and these vibrations are unique to each functional group. Each bond has a unique vibration, which allows you to use it as a signature. The FTIR spectrometer consists of a source, interferometer, and detector, and in addition to mid-IR, far-IR, near-IR can be advantageous for certain samples. Transmission may be good for solids, liquids, and gases. Specular reflectance is good for smooth samples. Diffuse reflectance can be used with rough solids, powders, and salt molds. And ATR is the simplest technique in terms of sample preparation and works with liquids or solids. And I thank you for your time and take any questions.
Okay, thank you, James, for that excellent presentation. So I just want to let you know that you are going to receive a link with the slides and the recording of this webinar. And also you can post your questions, and we are going to be answering now. So James, I'm going to pass to you the questions that I see in the.
So where are the questions?
I'm sending you the questions.
Okay.
You can read them in the panel of questions.
Oh, okay. So could a transform other than the Fourier be used? I guess hypothetically, you can actually save the interferogram, and then in your own software, you might be able to use a different transform. It's not, I'm not sure why you'd want to, but that would be the solution. You can save it, the interferogram, and use the interferogram to do your own method. Okay, highest transmission should be between 95 and 100%. Saturation should be avoided. Correct. So you should avoid the highest transmission. What I was talking about was the portion of the spectrum where it's flat, not where the peaks are, but where it's flat should be between 95 and 100%. And the saturation is the peaks. So the peaks shouldn't go above 5%, because once you get there, you start saturating the detector, which causes issues. What would you consider the best in-class testing of the spectrometer to show it's working properly? Polystyrene's the gold standard. I would use that. I would also look at the, I always recommend customers write down periodically. So if you have a log book on who's used the instrument, I always say you should write down the interferogram. It's got an intensity associated with it. It's a number. And I suggest putting that down, because that will give you some indication of the health of your source and your spectrometer. But yeah, really, the polystyrene is the gold standard. That's what the pharmaceutical industry uses. So what causes the difference in the FTIR peaks for calcite compared to aragonite? So they have it's a different crystal structure. So trying to remember, I don't remember the crystal structures of the two offhand, but you can imagine an octahedral and a tetrahedral will have the same functionality, like metal oxygen bonds, but since they're in different configurations, they're going to have different energies associated with them, and different modes would be allowed versus not allowed. So the difference in the FTIR peaks are that metal oxygen metal bond that's occurring. Hey, Carlos, is it okay if I trash the answers to questions after I do them?
You can scroll down.
Okay. You have problems with reflection off the surfaces of the diamond cell. No, the diamond it's pretty, once you squeeze it down, they're going to be parallel. I know what you're saying. So that air gap, the air gap, I've used it a few times and I've never had an issue with the gap between the diamond windows. But I do understand what you're talking about. Yeah. In which cases, while working with FTIR regions, we should advise vacuum to customers? Just for asking, just analyzing some inorganic samples in the FTIR region, does the customer need a vacuum option? It really depends on your sample and on your lab. If your sample is strongly absorbing, you might be able to get away with just a purge, but you need to at least have a purge. And one thing that could be done is we could just run the samples and see. It's always best to run the samples before you get there. Is ATR FTIR a qualitative technique, or can quantitative data be collected as well? How can the sample be prepared to determine the relative or absolute concentration of the different functional groups? So it can be used quantitatively. One of the things I like about ATR is, again, you know the path length, right? So since you know the path length, then that will fit into Beer's law, and you can use it to actually create a concentration curve. So with the concentration curve, you want 5 data points that span the range of the samples you're going to be looking at. Listen up, sorry. Why is it doing that? Yeah, so the relative or absolute concentration of functional groups, again, if you have a concentration curve, then if you can make a concentration curve with the different functional groups, you can look at them. You may want to use a secondary technique to verify the concentrations before you do it, but ATR is a very fast way. I've had a lot of situations where people have a lot of GCs and they have these routines they run that takes a half hour, And they use that to standardize against an ATR, which takes, 5 minutes. So you've showed in the sample preparation section, press samples between diamond different than KBR. What is the advantage of this technique compared to the KBR press? So the biggest advantage there is that you've got the sample prep. You're not having to grind the sample and make a pellet. So it takes at least a half hour to make a pellet. However, the diamond cell, you just put it on in between the two windows and crank it down. So it takes 5 minutes to do a diamond anvil cell versus KBR pellet. Is it possible to use in the far IR region? I've not done it, but I mean, theoretically, diamond goes down to 50 wave numbers. No, 150. It goes down to barely 50 wave numbers. Really, 150 wave numbers is where it starts losing most of its energy. So it's possible your cutoff's going to be a lot higher than if you did like regular P windows in a cell. Can quantitative analysis be carried out in solid non-transmitting samples using ATR FTIR? The answer to that is yes. Can FTIR distinguish between carbon powder, carbon filler, fiber, and graphite? The answer to that is mostly yes. I'm not sure about the graphite, how well it shows up in IR. I've never tried to do graphite in IR. A lot of times, Raman is really good for these kind of samples, but you can tell the difference between, well, as long as the carbon powder and the carbon fiber, if they've got the same structure, you're not going to be able to tell the difference. So this is one where you may want to actually think about a different technique, and I would go with Raman on it, because it can definitely tell the difference quite strikingly. Can FTIR be used to measure emissivity of a solid at a given temperature? Yes. So you can actually have as an external source go into the detector. Again, it's going to depend on how emissive your sample is, but it's not impossible. We can talk more about that if you want to contact us. For alignment, what type of mirrors are used? So I did mention that we use cube cornered optics. So the advantages of the cube cornered optics is that if the mirror moves at all, it doesn't change the beam path. If you have flat mirrors, then what happens is that the light tends to stray, so that companies that don't use cube corners have to constantly adjust their mirrors. They have to constantly align their mirrors to get it to be a straight beam path. We're interested in HC and OC ratios in plastic polymers. Can we look at major CH stretch and CO stretch divided by the carbon stretch to get these ratios? Would we use drift on plastic sheets? I would just go ahead and use ATR. And yes, you can actually get the peak areas and divide and get the ratios that way. Does Beer's law work for any samples, gas and solid as well? Yes, so Beer's law can be used for gases and solids. It's all a similar idea. You have a certain amount of absorbance that's related to concentration. Okay. In the IR quantitative analysis slide, the chart shows the regression for Beer's law not intercepting the origin. Is this common? It is actually fairly common for that to happen. You can do some mathematical tricks to force it, but it's not recommended. Can you please explain and guide me to how I can get a black body single beam profile of the ceramic source? So the single beams, you just save the single beam. That's all you have to do, and then you can open the single beam and look at it. And that will be your, for the background, is going to be your profile of the source. For solid samples, does powder versus centered make a difference? So I'm assuming you mean centered or all together. Most of the time, no. If you've centered it using heat, then you may actually change the structure, like the macro structure, not the individual molecular structure, but how they interact together, which that can cause a change. So it'd be like a polymorph. You may create a polymorph during the centering process. But as long as you don't do a polymorph during the centering process, then you're okay. For quantitative analysis, you recommend ATR or transmission. You can use both. ATR works well enough. If the ATR works, I'd go with ATR. Transmission, creating samples is pretty challenging, and you're going to have the right mass every single time in your mole, and that's kind of hard to do. So I would probably go with ATR. Special care with samples and spectra treatment for building concentration absorption graphs. So the samples, you want them to be, if you're using ATR, you want them to be flat against it. That's one thing. You need to be hitting the same path length every time. I would use the range that you expect to see with your samples later on, and I would go with the range anywhere between 10% and 90% of whatever you're looking at. And again, that zero it's not necessarily going to cross the zero axis. So, and then I usually do, for concentration, I do peak area. What solvent do I have to use to clean up the sample holder on ATR? It really depends on what crystal you're talking about. And this is actually, I like this question because I probably should have had this in the talk. So you can use most solvents on diamond. And the common solvents I like, like ethanol works well, it evaporates quickly. Isopropyl alcohol works well. I wouldn't use water just because it doesn't evaporate. It's a strong absorber. And then plus, I want to go into this because it really probably should have had that part of the talk. But when you're cleaning ATR crystals, you really need to use cotton-based materials. So you need to use cotton swabs, cotton balls, those Q-tips. Use something that's cotton. Do not use chem wipes. So chem wipes can actually hurt the zinc selenide and germanium. It's actually bad for the crystals because it's actually harder than the crystals. So avoid chem wipes on ATRs unless it's a diamond. Diamond, you're okay. How to select an angle of incidence for an IR reflection absorption spectrum. My sample is a monolayer on the metal surface. So if it's a monolayer on a metal surface, I would get a grazing angle accessory with an MCT. That will be your best bet. You can have variable angle reflection accessories too, but you're looking at a really small amount of material, and really grazing angle is going to give you the best. And you can actually put polarizers on it and get orientation information as well, which is nice. How to characterize the change in temperature of the ceramic source over time. So there's no direct way in the instrument to tell. However, like I said, if you use the interferogram, if you use that intensity is going to be directly linked to the intensity of the ceramic source. So if you have that in a logbook, you can actually see it go down over time, and you'll know. It automatically will tell you when it's time to change the source, but you'll actually see it go down over time. So I really, it's a good figure of merit to use that ZPD energy. One more question. What kind of solvents can be used to clean KBR windows while performing experiments with a liquid cell? I would use an organic solvent, maybe not hexane, but something like it, something that has no water in it. So I would use hexane. That's going to be your best bet. All right. So thank you for your attention. Carlos?
Sorry, I was in mute. There are more questions, but I think we can answer some of them offline. I just want to go back to one question because I think it was really interesting. I don't know if you read it. There is one question say when FTIR is coupled to a microscope, Cassegrain type objective are used. In this case, do the beam always hit the samples at a certain oblique angle in transmission and reflection measurements? The angle of incidence is going to depend on the Cassegrain. James is going to be making a presentation in 2 weeks about FTIR microscopy, and in that case we are going to be talking about the different objectives of the Jasco FTIR microscope. Nevertheless, a 16x Cassegrain, that is the magnification that we use, it has an incidence angle of 27 degrees, and for the Cassegrain of 32x, that's the other magnification that we use, is 32.5 degrees. If you're using a grazing angle we are talking about 75, 80 degrees of incidence of the beam. But this question is really good. I didn't want that we leave without answering that. There are more questions. Thank you very much to everybody. I'm doing my best to answer the question after offline. And I just want to finish today with an invitation. Next week is my turn to make a presentation about Raman imaging. I'm going to be talking about different features, hardware, software, how to get those beautiful Raman images. And the week after next is James coming back with more FTIR microscopy. So with that, I just want to say thank you and have a good evening, everyone.